In this video, I'm going to talk about the spherical harmonics. And the first few steps here in sort of deriving, I guess, the spherical harmonic function, I just took the picture right out of my notes here because there's just a lot of rewriting different symbols in different places. And so I'll just go through the first few steps here and then I'll start writing things down. So we start with this equation right here, which is, as you can see, a partial differential equation, a partial second order. So there's a second derivative here, differential equation. We can turn that into an ordinary differential equation using separation of variables. So the first thing to notice here is that we are in polar coordinates. So we had to go from our usual Cartesian and convert to polar coordinates. And as you know, well, maybe you don't, but I would hope by this point you do. Polar coordinates in 3 dimensions have the r, the theta, and the phi. So the r is the radial component. Uh, these are the angles. There's one I think called the azimuthal and maybe the latitudinal. I forget what they're actually called, but so it's essentially saying that if you have a sort of 3D coordinates here, the radial is sort of the length of our vector, and then I think the theta is sort of this this component of it, and then the phi is that component. But anyway, what you will notice here though is that we don't have any radial components in this equation, and so the radial components will be handled once we get to the Bessel functions. So right now we're just worried about our theta and our phi, which the theta will be between 0 and pi, and the phi will be between 0 and 2 pi, which allows us to cover like a whole sphere around this. But anyway, we do our separation of variables, which is essentially just taking our psi here, which is a function of the theta and phi, and separating it into something that has, so I'm using the uppercase theta, which for me just means writing it really big, which is a function of the theta multiplied by the phi. So this is the uppercase phi here, which is a function of our phi. So it's just separating this into the product of two different functions, one being of just this single theta variable and one of this single phi variable. And so from there we end up with this equation right here. So we've separated everything out. So now we have our uppercase phi's and our uppercase thetas here instead of our psi's. Then we divide through by the product of the large theta as a function of theta and the large phi as a function of phi, and multiply by both sides by sine squared of theta, and we end up with this. So we have this sine theta over our function theta. So you could probably put a little function of theta here if you wanted to. This is a function of our phi here. But anyway, so what you should notice now though is that we have all our thetas in this term here and all our phi's in this term. Well, we have this theta here, but it's in it's in a term separate from the phi. So we have the thetas and phis separated, such that we can rearrange it so that we have on one side of the equal sign everything that has theta in it, and on this side everything that has phi in it. And so that will allow us, because in here, because these are equal to each other and the thetas and the phis are independent, this can only be true if these are both equal to a constant. And so we can do that. So I will call this this equation 1 because I'll have to refer back to it. And that will be sine of theta over our large theta, which is our function here, times d theta times, or acting on, I guess, sine of theta d large theta. I'll draw that even larger just to make sure that that is that can be seen to be the function here changing with respect to the independent variable there, plus our L times L plus 1 sine square theta, and that will be equal to some constant which we are going to call m squared. And we will see why that makes sense. Why that makes sense in a little while. But we can rearrange this around such that we have 1 over sine of theta d theta times sine of theta, or I guess this is an operator, so acting on sine of theta d big theta over d theta, and that's plus L, that should be an L, sort of a fancy L there, times L plus 1 minus m squared over sine square of theta. And then that's multiplied by our function big theta there equals 0. So now we've set this sort of in terms of being equal to 0. And so then if we look at the other side of this equal sign up here, I will call this equation 2. So this is just setting that equal to the same constant, this same m squared constant, and that will be minus 1 over uppercase phi here. Draw that a little better. So phi times the second derivative of uppercase phi with respect to lowercase phi here, and that equals m squared. So we've just kind of taken these two things apart and just set them both equal to the same constant. And we could also rearrange this so that we have the second derivative of our phi function. Remember that these uppercase Greek letters are all functions. Remember that the big theta is a function of the little theta, and the big phi is a function of the little phi. And so that is taken with respect to the little phi. And we can just say that that is equal to minus m squared times the big phi. All right, and so this number 2 here has a general solution, which will just be, so our big phi here, and that is a function of little phi, because that's a function, will be equal to, so this is the general solution, e to the I m little phi, so the I being the complex number, the imaginary number, plus b e to the minus I m phi. So we have this as our general solution to equation 2 up here. And we have to have it so that that the uh, the phi at 0 is equal to the phi at pi, and this can only be true if m equals an integer. And so that is sort of an initial condition, perhaps you could call it, that's that's being imposed on the solution to the phi here. But now, if we go back to 1, so with our equation 1 up there, we make a change of variable. And once again, I've mentioned this in previous videos, this is something you see just all the time. I mean, especially once we actually get back to the quantum mechanics, you're going to get sick of all these changing of variables and sort of setting different things equal to, setting some big long equation with a bunch of stuff in it equal to some letter, and we're going to be doing that all the time. So it's just one of those things you have to get used to, and it's something that's done so that we can get things into the form that we want it, and that's pretty much exactly why we're doing this change of variable. And we're doing the change of variable so that cosine of theta is equal to x. And this allows us to have dx equal to minus sine of theta, which well, this should also have a d theta, because we're essentially saying that dx d theta is equal to minus sine of theta. But anyway, this also allows us to say that 1 over sine of theta times 1 over d theta is equal to minus 1 over dx. And so then we can say that if we have sine of theta d theta is equal to sine squared theta times minus d dx, and this allows us to say that we have 1 or minus 1 minus x squared d dx. And so this right here just comes from the fact that if we have sine squared of theta plus cosine squared of theta, that equals 1. So if we just subtract sine from both sides, then we have 1 minus sine squared of theta equals cosine squared of theta. Well, I think this is doing it the other way around, but anyway, it allows us, when we have this this x is equal to cosine of theta, that we can get to this 1 minus x squared of theta. And if you've watched my videos so far on the Legendre polynomials and the associated Legendre functions, this 1 minus x squared should be familiar to you, because this allows us to get our associated Legendre equation, which we have as d dx times, or acting on, I guess, 1 minus x squared d theta dx plus our L times L plus 1 minus m squared over 1 minus x squared multiplied by our function here and equal to 0. So this is the associated Legendre function, or associated Legendre equation right here. So that's what all this change of variable was, is so that we could get everything to look like our associated Legendre equation here. So that's what that's what all this was for, was in order that we could get the theta, this number 1 here, this theta part of the equation, and that was the reason why we had it equal to m squared here as well, so that we could get it in the form here of the associated Legendre equation. And so this will have a finite solution at 0 and pi, only if L is equal to an integer. And so from here, the solution to this, I guess we could say, is so our big theta here, which is a function of theta. Well, we have it as a function of x right now because of that change of variable, is going to be, so we know from the previous video that solutions to this associated Legendre equation are the associated Legendre functions. So P, L, M as a function of x. Then after we do the sort of change of variable, well, we said that x was equal to cosine of theta. And so that's how we get to our associated Legendre functions here as a function of cosine theta. And this here is the form of the associated Legendre functions that we will be pretty much working with exclusively. So this just comes about because we had that change of variable of x equal cosine of theta. And so we can say that the solution, when we sort of go back to our psi, remember that we got the theta, the large theta and the large phi from that separation of variables. So this is the psi was the function of theta and phi, which was, as we remember, the theta as a function of, or the uppercase theta as a function of the lowercase theta multiplied, or the product of it, with the uppercase phi as a function of the lowercase phi. So since we have our solutions, we have this as a solution for the uppercase theta, and we had this as a solution for the uppercase phi. We can just take the product of those, and that will just be the product of our solutions. So that will be our a e to the I m phi plus b e to the minus I m phi multiplied by our Legendre function, which is a function of cosine theta. And so if we just distribute that Legendre function through, we end up with, well, we will also do a change of these a and b constants. So if we just have an a1 equal to a, and we have an a2 equal to minus 1 to the mth power times L plus m factorial over L minus m factorial times b. And so this is, I believe, just sort of a normalization thing here. So we're just putting the a2 here instead of b. And so what we end up with after we make this change and multiply or distribute this through is we end up with a1 e to the I m phi times this associated Legendre function here, cosine of theta, plus a2 e to the minus I m phi times this associated Legendre function. So we're actually going to have minus m up here and a function of cosine theta. And so this is all equal to our phi, or our psi rather, which was a function of theta and phi. And so what you will often also see is that these terms here will be sort of, once again, we sort of just simplify it down to sort of a single symbol, and that will be YLM is equal to e to the I m phi times the associated Legendre function here, which is a function of cosine theta. And so we will see something like this, which will make this equation, which will turn this equation into something that looks more like a1 y lm plus a2 yl minus m equals psi of theta and phi. And so once again, this is that thing I was talking about where in quantum mechanics and differential equations in general, they're always trying to take these more complicated things and just set it equal to something a little bit simpler. So there's lots of changing of variables, lots of setting, larger things equal to some smaller thing, and it's just one of those things in math that makes it more confusing to learn, but something you just kind of have to get used to. And so I've been using this lowercase y here because what you will often see when you're looking at these spherical harmonics is we will have an uppercase y lm, which is equal to some multiple of the lowercase y lm, such that I'll just write st, such that it can be normalized. So it'll just be some multiple of our solution here, uh, which can be normalized. And the normalization we want is of the form uh, from the integral from 0 to 2 pi of d phi times the integral from 0 to pi of d theta sine theta times our uppercase y here, which is sort of the form we're going to be using from now on, L m, and that is a function of theta and phi. And this is the complex conjugate multiplied by y L m prime. This is an L prime, as a matter of fact. Theta phi, and that will be equal to the Kronecker delta of L prime times the Kronecker delta of m prime. And so we want it to be normalizable so that this will be true, and that's why we use the uppercase y version. Uh, and so, yeah, this was, I guess, the derivation, if you will, of this uppercase y ml. And so that is going to be our spherical harmonics. Uh, so theta phi. So it's a function. It's a function that satisfies that differential equation, which we went through pains to get into the form of the associated Legendre equation right here. So we went through some pains to get our spherical harmonic equation, which was this original one up here, which was a partial differential equation. So we used separation of variables to make it into an ordinary differential equation, and then we could get these two equations here equal to this same constant m squared. We used m squared so that and then all of this change of variable stuff so that we could get it in the form here of the associated Legendre equation, and that allowed us to have solutions where we have the associated Legendre functions here, and that allowed us to get to this symbol here, which is the symbol for the spherical harmonics. And so down here I just have, so this is often how you will see the spherical harmonic symbol, which we just got right here. You'll see it written like this. So we have our associated Legendre function here. We have our e to the I m phi here. But then we have this right here, which is a normalization. A normalization. And so I have this here, which I just copied off of a website. I'll leave a link to this in the description below. But the outline will look something like this. It says, so we have our spherical harmonic, and we're setting it equal to this stuff right here, multiplied by a, which is some unknown normalization constant. And we require our normalization to be this, which is exactly what I was talking about up here. So that is just that. They're just using different variables. They're using this k and l and m and n here, rather than using the L, m, and then L prime, m prime. And so we separate this integral over theta and phi because they're independent. We end up with we'll evaluate the phi integral than the theta integral, and this is what we end up getting, this 2 pi, and then all of this stuff right here, which is what you get when we take the integral of the product of these two associated Legendre functions. And so that's if these are the same associated Legendre function. That's what this Kronecker delta here is telling us. And so that's how we end up getting this right here, which you can see is the reciprocal of what we have right here. We have the a squared there, and so the a will be equal to the so we're just dividing both sides by all of this right here, and so and then taking the square root. So a will be equal to the 2l times the or 2l plus 1 rather, plus 1 times the l minus m factorial over, so now it's this numerator goes to the denominator because we divided both sides, so 4 pi 4 pi times the L plus M factorial, and that will be the square root. So that's where this where all this sort of mess comes from right here. And so yeah, that is the how we get this normalization right here on the spherical harmonics. And so the last thing I wanted to talk about is sort of what do the spherical harmonics kind of mean, I guess. And so maybe a good sort of way to think about it intuitively is you could think of the unit circle as sort of a circular harmonics. And the functions for circular harmonics are just the sine of theta, the cosine of theta, the tangent of theta, and you know the secant, cosecant, cotangent, all that. So this would be circular harmonics, and we know that that works because if we if this vector here sort of keeps moving around counterclockwise, and we plot that as a function of theta, we get these sinusoidal waves here. And spherical harmonics are essentially the same thing, but instead of on the surface of a circle here, it's on the surface of a sphere. And perhaps you could think of the spherical harmonic function here of theta and phi as being sort of equivalent in spheres to what things like the sine of theta and cosine of theta are in circular harmonics. And so this is on the surface of a sphere, and this is on the surface of a circle. And so that is how with spherical harmonics you get, so this is just on the Wikipedia for spherical harmonics. And if we kind of go down here, so this is what it looks like for these different values of L and M. So we see that we have plus minus, which is similar to what we have here on circular harmonics. So our x-axis would be here, and we are going between plus and minus and plus and minus. And so that is what is actually happening on the surface of these spheres for these different these different values for L and M. So putting different values for L and M in our spherical harmonics gives us these different sort of functions on the surface of a sphere. And so you can think about the plus and minus on here being similar to the plus and minus on sort of a sine or a cosine function here for circular harmonics. And so that is hopefully kind of an intuitive understanding of what the spherical harmonics are actually talking about. Um, and so having these different L's and different M's you can see is sort of changing, well, in 3 dimensions we kind of have different directions. You can go one way around the sphere or the other way around the sphere, where in circular harmonics there's basically just this one way of going around the circle. I mean, you can go the reverse way, but it's just the same thing, but kind of a change of signs. But in spherical harmonics, you can sort of go around the equator or around sort of the meridian, I guess, on the surface of these spheres. But you can also see that that you can have essentially different frequencies going around here. So this one, you can see we have sort of a plus minus in this frequency going sort of from top to bottom, where if you were looking at top to bottom on this one, it's just one plus and one minus, so it's sort of like a longer wavelength going from top to bottom. And so we will run into this. So, I mean, if you've already sort of encountered this, you probably know that the L and M are representative of quantum numbers. And so that's where the quantum numbers come from in these spherical harmonics. But anyway, I hope that gives a little bit of a intuitive understanding of what the spherical harmonics are. If we think about it in terms of something that is a little bit more familiar to us, which is these circular harmonics. But anyway, I hope you found this video helpful, and I will see you in the next video.